Now let me introduce a concept called escape speed. For example, if this is Earth, and obviously this is radius of the Earth, and we assume mass, gravitational attraction mass is concentrated right here. Now if there is a space vehicle or a rocket on the surface of the Earth of mass m, now we want this space probe goes to Mars. So theoretically, this space probe should escape Earth's gravitational field, which means, relatively speaking, it's not going to be trapped by the Earth's gravitational force. It's going out. So the question is, what is the VESP? What should be the escape speed? How large the force has, speed has to be, then this rocket will be able to get out of the Earth's gravitational field. Why we need high speed? Because if we have a high speed, and then the rocket will be able to going up, but gravitational force will try to decelerate. So we'll have to let this guy keep going to very far away when the gravitational force is so weak there's no more deceleration. And that moment, if we still have a little bit speed left, then we escape. So the extreme condition is we start with a V escape and going far away from the center of the Earth with deceleration, because Earth's gravitational force will decelerate. So the speed will slow down, slow down, slow down until to the edge of the Earth's gravitational field. The speed is 0, but no more gravitational attraction force from the Earth. And then we say escaped. So this is a rather difficult situation if we try to use force, because force changes magnitude all the time. So therefore, the deceleration is not a constant. But if we use energy to deal with this problem, probably that would be easier. Let's say that right here, what is the total energy of this rocket? Don't forget, if we talk about mechanical energy, we have to consider about the kinetic energy plus potential energy. In this case, potential energy is the gravitational potential energy. We learned that the gravitational potential energy between 2 point masses is that gravitational potential energy equals to negative g of first mass times second mass divided by their separation. Now, if this is a spherical symmetric object that we can view gravitational attraction masses right here, then their separation will be 1 RE. So the gravitational potential energy of the rocket has right here is negative capital G, mass of rocket, mass of the Earth, and their separation is 1 RE. And if the rocket has escape speed, so it has kinetic energy 1/2 of m VESP of squared. That's the total mechanical energy when the rocket is near the surface of the Earth. And then when the rocket is going very, very far away, very, very far away means r is almost equals to infinite with respect to the radius of the Earth. So when this r is infinite, the gravitational potential energy from the Earth will be 0. And also I explained that when you reach there, the speed is almost 0. So at that escape, the edge of the Earth's gravitational field, potential energy is 0, kinetic energy is 0. Why we have initial mechanical equals to final mechanical energy? That is because there's only, if we ignore the friction of the rocket has experienced with the Earth's atmosphere, which is very briefly, then there's only one force between the rocket and the Earth, that is gravitational force. Gravitational force is a conservative force, so the mechanical energy of the system is conserved. So we can easily discover that this m, you can actually, both sides of the equation divide by this little m, it's gone. And we rearrange this negative term to the other side. So we can have VESP equals to twice capital G mass of the Earth and divide by radius of the Earth and square root. If we plug in the proper number for capital G, 6.67 times 10 to the negative 11 of SI unit, mass of the Earth is 5.98 times 10 to the 24 kilogram, and RE is 6.4 times 10 to the 6 of meter. And we can find that escape speed, in order to escape Earth's gravitational field, it comes out as 11.2 of kilometer per second. The rocket must have enormous speed to escape the Earth's gravitational field, because every 1 second it has to be able to travel near 11 kilometers. This is a very interesting situation. If you still remember the problem that we encounter between a ring, a point mass. Okay, let's look at the situation again. This is a ring of mass capital M, radius r. This is a ring, so it's one-dimensional. Again, the linear density mu can be calculated by total mass divided by the circumference of the rings, 2 pi of r. Now the question is, if I have a point mass of little m at the center of the ring, well, if this little m is at rest, then it will be at rest there, because the gravitational attraction of the ring to this m is 0. Because it just, imagine if here's a dm, it's going to point out this way, and the other will put opposite direction, same magnitude. This cancels out. So this guy will be very peaceful. However, if the question is, how do we let this little m escape this ring? Then we have to let this one acquire a VESP, just like the problem we discussed before. How large has to be the escape speed that we can get out of this gravitational field of the ring and going very far away? The problem is, well, we have to think about this. If this m reaches here, it still has a little speed left. And we hope that it will continue to go to further away. And right now, we know that if little m is right here, there is a gravitational attraction from the ring towards this direction. And we actually obtained that formula. And we can take a look at it. We got it. The gravitational force between the ring and a point mass of a distance a away from it is this. So be careful, this a right now is a variable. So we have to rewrite it. Now how do we rewrite it? The gravitational force right now, I should write as F of G, that is between the ring and point mass, equals to of capital G, little m, and the ring, and divide by, well, there is, let's make this is a variable x, because it's x meters away from the center of the ring, so that will be x, and then the denominator will be at r squared plus x squared and 3 to the 2. And that is the gravitational attraction between the little m and the ring. So the gravitational force is rather complicated. As you can see, when the little m goes further away, when x gets larger and larger, the gravitational force will be weaker and weaker. But anyway, there is a gravitational attraction. If there is a gravitational attraction, there must be a potential energy. Now, how do we write the potential energy of point mass m x meters away from the ring? I think we cannot use the previous one, because the one we got for the spherical symmetric distribution is potential energy, we learned from the previous case, is negative g m1 m2 over separation. But now this is not a spherical distribution, so we have to start from scratch. How do we do that? That is this. Work done by gravitational force should be expressed as work done is F of G dot D, in this case is dx, because we only move in one direction, work done equals to the negative change of potential energy. Change is the potential energy final minus potential energy of initial. So from there, we can find our potential energy initial final. So we have to work on it, and let's take a look at what's going to happen. Fg is this way, and our dx is opposite. So this dot production gives us a negative, and we're plugging Fg expression, capital G mm of x over r squared plus x squared of 3 over 2 of dx. That looks pretty good. Why is that? That is because we have a x dx. If we time it 2, divide by 2, then we can have a situation. Here's a negative sign. G comes out, little m, capital M. And this 2, these are constant. And if I regroup 2x dx, that will be dx of square. And denominator is r squared plus x squared of 3 to the 2. As we know, because r is a constant, actually we can do that. So this gives a situation as, well, constant still remains in front of that. We have something like r squared plus x squared. If we bring denominator to the numerator, it's negative 3 over 2 of d r squared plus x squared sum integral. So for this integral, the result should come out as 1 over the coefficient is negative 3 over 2 plus 1 and r squared plus x squared negative 3 over 2 plus 1, right? Let's continue. So the result is the gravitational, the work done by gravitational force equals to negative g, little m, capital M over 2. And the coefficient is, as a matter of fact, plus 1, 2, 2. That will be a negative 1/2 on the denominator, so it's a negative 2 right here. And then we have this negative 1/2, so that will be r squared plus x squared of this one, negative 1/2. From where to where? Well, obviously, let's say from point of x to infinite. When we plug in that infinite, that this is this will be a 0. And then when we plug in x, that will be this. So as a matter of fact, as we can see, the result is negative 2, negative 2. This cancels out. So this will be of GMM, a situation of final, that is this, minus initial is x meters away, so r squared plus x squared, final minus initial, that's that. If we compare this to the work done by gravitational force, equals the negative change of that u final minus u initial. As a matter of fact, what we can do is we need a negative here. So we need a negative here and there. See, this, there. So, see, it's negative, negative. Final is this, minus initial. This tells us u final is negative r squared plus infinite square root. U initial is negative, that's that, r squared plus x squared square root. What does that tell us? That tells us when the little m is x meters away from the ring, its potential energy u of x is negative, as we can see right here, right? Let's not forget about our constant here, GMM. So it's negative GMM over r squared plus x squared square root. That is the expression of the, I should add this constant here, GMM, GMM. So that is the potential energy right here. So since we know the potential energy right here is this much, and we assume, if we assume x equals 0, then it will bring this guy to here. So the potential energy at the center of the ring, see, when x equals 0, it doesn't equal to 0. When x equals 0, it comes out negative GMM over R. Isn't that interesting? The gravitational force between the ring and M, if M is at the center of the ring, is 0. But it does have a potential energy, which is, when x equals 0, negative GMM over R. And then this has a escape speed. So the energy right here we can write as kinetic is 1/2 mVESP squared. Potential is negative of GMM over R. This is the total mechanical. If we want this one to go further away, well, how far away? Infinite far away. As we learned, when it's infinite far away, this will be 0, right? Because this denominator is so big, it's 0. Potential 0, you barely reach there, no speed, so it's, at the end it's 0 plus 0. So from here, you can find escape speed. So little m again, both side equation divide by that. You can find VESP equals to F twice GMM over R square root. Very interesting result. Let's look at another problem. Along the x-axis, we have Earth located at the 0 of the x, and we have Earth's moon distance, and we have a moon located here. Question number 1 is, at which point between Earth and the moon the gravitational attraction from the Earth and from the moon cancels out? Well, Earth is very large. Earth has 100 times mass of the moon. Therefore, I guess this is the point that the gravitational attraction from the Earth, which is this way, F of E, cancels with gravitational force from the moon, which is F of the moon. Because for large mass, you need a larger distance to get equal magnitude a smaller mass attraction. So gravitational attraction between the Earth and, let's say, the mass of a space probe is little m. So the gravitational attraction of F of E equals to capital G, mass of the Earth and mass of the space probe divided by x meters. That is the distance between the Earth and this particular location. So separation square. And gravitational force from the moon to the space probe, F of the moon equals to capital G, mass of the moon, mass space probe, and what's there left? That is the Earth's moon distance, subtract the x and square. So if we want to find this x, which is where between the Earth and the moon that the force from the gravitational force from the Earth cancels gravity from the moon, then we just let this one equals that one. We can solve this equation for the x. Assume we already solved that. Now the question is, what is the minimum speed that we need to give to this space probe, that we can let this space probe get into near the moon and then start to circle around the moon as a moon satellite? We need to approach this problem by the energy method. Let's ask this question. What is the total mechanical energy of this space probe at the initial position? It is under influence Earth's gravity. So it is gravitational potential energy between the space probe and Earth. It is also under the influence of the moon. So we have negative g mass of the Earth, mass of space probe over x. That's potential energy between the probe and Earth. Potential energy between the moon and space probe. That is RE of the moon subtract x. That's the potential energy between space probe and moon. And we ask for what is the minimum of speed it requires. So we give a speed 1/2 mv minimum. That's the total of mechanical energy at that point. Now, if we allow this space probe to be a near moon satellite, let's say the circular orbit is almost near the radius of the moon, then once that happens, it certainly has potential energy. Let's say near the moon will be negative of g mass of the moon space probe RE of the moon. If we still think it is under Earth's influence, then we have negative g mass of the Earth, and this is now how far away from the Earth? A moon Earth distance away. That is 2 turns. And then plus the kinetic energy, because this satellite is orbiting. So 1/2 of mass of the space probe, v of the orbital speed square. Now, as a matter of fact, we learned that before. Something circle around, something is in the orbit due to the gravitational attraction of a spherical object. The combination of these two terms actually comes out as this can be replaced by that. The total mechanical around, if something is in a circular orbit around a spherical symmetric distribution, total mechanical is this much. So as we can see, throughout this equation, mass of the space probe cancels. All we need to do is, since from first step number 1, we already solved x, so x is unknown. All we need to do is now we're going to solve what's the minimum speed we need to give to the space probe, because right now the space probe is at rest because Fe cancels with Fm. Now we need to give a little bit of boost, okay, and we need to give a minimum speed. So once space probe moves towards the moon, then moon force will be larger than the Earth force. It will start to approach the moon. So eventually it's going to settle into the orbit very close to the surface of the moon and become a satellite.